Hey everyone, I'm going to be talking today about training neural networks. And specifically, I'm going to provide a variety of general details about how to train neural networks. And then later in the course, when we get to applications, we'll talk more about specifics of specific architectures. All right, so first I'm going to say a word about data preprocessing. We need input data to be zero-centered and on the same scale. With image data, we don't typically worry about putting data on the same scale because an RGB image is by construction on a scale between 0 and 255, but we do want to zero-center the data, and there's two options for this. You can subtract the mean for the image, which is essentially an orange blob. AlexNet does this, or you can subtract the per channel mean, which would be three numbers. VGG does this. All right, so that's straightforward. Initialization. This is actually really tricky and was part of the reason why deep learning in the early decades had disappointing results. So if you start out with weights that are too small, the neurons will have close to zero value, and this implies a zero gradient because the gradient is just the activation times the upstream gradient. But if the weights are too large, you'll saturate the network, and the gradient flowing through the network will all be zero, so you can train for a long time and the loss won't move. So there's something called Xavier initialization, where you divide by the square root of the number of inputs to the neurons. If lots of weights feed into a neuron, then the initial weights will be smaller. And so this was kind of traditionally what people used, but it doesn't work that well for ReLU, which kills half the distribution by setting it to zero. So there's something called He initialization that adjusts for this by drawing weights from a normal distribution centered at zero with variance 2 over n. In practice, oftentimes you're going to initialize your model with learned weights from a pre-trained model. And so if you're doing something with a language model, you might start with the Roberta weights from their final checkpoint. Or if you're doing a vision model, to do vision classification, you might start with an ImageNet pre-trained backbone. But if there are weights that you need to randomly initialize, this would be how it's generally done. All right, optimization. So neural networks, and especially deep ones, as is kind of obvious, are really challenging to optimize. It's a complicated space. You could have 100 million or more dimensions. You could have 1 billion dimensions. And so the Grant Sanderson videos that I recommended as a graphical introduction to neural networks showed stochastic gradient descent. In reality, you wouldn't use plain vanilla stochastic gradient descent. And so let's think about what the challenges to optimizing a really complicated function are. So first of all, there is pathological curvature, which refers to regions of the loss function that aren't scaled properly. These are often called valleys or trenches or ravines, and they're quite common near local minima. And so to understand why this is a problem, it's helpful to note what happens with a one-dimensional function when the learning rate is too small or too large. So you can see if your learning rate is too low, you will converge very slowly. If your learning rate is too fast, you can oscillate back and forth and diverge. Okay, so what happens, in valleys? Well, you tend to oscillate back and forth in the steep direction across the slopes of the valley and converge very slowly in the shallow dimension, making very slow progress along the bottom towards the optimum. Another optimization challenge is saddle points. In a 100-dimensional function, it's actually much, much more common to be in a saddle point than to be in a local minimum. Which I guess is kind of intuitive when you think about it. And so how do we address this challenge of pathological curvature plus saddle points? And so essentially what you can do is add a momentum term to stochastic gradient descent, where you build up velocity as a running mean of gradients. And rho here is known as the friction parameter. We would typically set it to either 0.9 or 0.99. Okay, so you take a gradient step as you would with stochastic gradient descent, but then you also have a momentum step, which is from this running mean of your past gradient, and that gives you your actual update. So why is this helpful? Well, momentum increases for dimensions whose gradient point in the same direction, and it reduces your update for dimensions whose gradients change directions. And so it helps with oscillation, because when you're oscillating, your gradient is changing signs. And when you average over that, then it's slowing down that oscillation, whereas it will speed up convergence in the dimension where you are not changing directions, which helps you get to the optimum faster. It can also help you escape saddle points as long as momentum is not only in the direction of the minimum. All right, sorry about that. Okay. So you might be concerned that momentum would push you out of a sharp minimum, but that's actually a feature and not a bug, because flat minima tend to be more robust to generalization. All right. So we know that momentum will take us to the top of the green arrow shown here with your momentum step. And so what Nesterov does is to calculate the gradient there. Usually your update then will be a little bit different than it would have been if you calculated the gradient where you were initially. Okay, so momentum solves the challenge of valleys by changing the gradient, making it smaller in dimensions with oscillation and larger in dimensions with consistent movement in the same direction. We could achieve something similar by allowing the learning rate to scale differently in these dimensions. So this is what RMS prop does. It scales the learning rate by the exponentially weighted sum of the squared gradients, which yields a lower learning rate in dimensions with steeper gradient and a larger learning rate in dimensions with smaller gradients. So we commonly set beta to 0.9 or 0.99. And so there's something that combines momentum and RMS prop, which is called adaptive moment estimation, or ADAM. In full implementation, there's also a bias correction term that affects the first few iterations. And ADAM tends to work really, really well. It's the thing that you're most likely to see used, and most likely what you will use in practice when you choose your optimizer. All right, so you might be asking, why don't we use second order methods, like Newton's method? We could take a second order approximation of the gradient and update to the minimum of that function, and then we could just avoid altogether needing to choose a learning rate. Well, to think about why people don't do that, think about inverting a 100 million by 100 million matrix, or at the extreme, a 75 billion by a 75 billion matrix. That's not obviously not realistic. And so in practice, second order methods in deep learning are just completely infeasible. And in practice, you're very likely to use ADAM. All right, regularization. And so the idea behind regularization is that your model should be simple. You want to improve performance on unseen data, and you can do that by making, forcing your model to be as simple as possible. And so that's what regularization aims to do. A common type of regularization traditionally was called L2 normalization. And so it computes the Euclidean norm of the weights, that is the sum over all the squared weight values. And this regularization term is weighted by a scalar mu divided by 2 and added to the regular loss function, where mu is a hyperparameter known as the regularization rate. So what L2 normalization does is to favor putting small values on mini weights as opposed to large values on a limited number of weights. Use all your inputs a little rather than letting some inputs be used a lot. And so this is going to push the weight values towards 0 since you're disincentivizing using some weights a lot, which tends to lead to a simpler model that avoids modeling noise. So the terms L2 normalization and weight decay are often used interchangeably in papers and in textbook treatments. And just a small note that there's actually a distinction between these when you're using ADAM, and I point to a reference here. However, kind of in practice, oftentimes we won't use L2 normalization. We have other methods for regularization. And so you can think more generally of regularization as adding some random noise during training. And so a very common type of regularization is batch normalization. So we talked earlier about how we normalize our input data, but what about activations for subsequent neurons? This led to a simple idea, which is that if you want your activations to be unit Gaussian, just make them so. And the paper that this was put forth in is now one of the most cited papers in deep learning. So the idea is to compute the empirical mean and variance independently for each dimension and then normalize, and then allow the network to squash that range where beta and gamma k are learned parameters. So in convolutional networks, filter weights are shared across the input range. Hence, it seems reasonable to normalize the output in the same way. The mean and variance are computed from all activations in a given features map for all images in the batch. So in other words, we compute one mean and one variance per channel and normalize by that. And so why does this work? Why is this such a commonly used and powerful approach? Well, the initial paper argues that batch norm helps because of covariate shift. So the gradient tells us how to update each parameter under the assumption that the other layers don't change. But in practice, we update all of the layers of deep networks simultaneously. And the distribution of each layer's inputs change during training as the parameters of the previous layers change. And so this necessitates a lower learning rate and careful initialization. Batch norm significantly reduces the problem of coordinating updates across many layers, which stabilizes optimization and speeds up training. However, it's still debated exactly why batch norm tends to work so well. It's been argued that it smooths the optimization function, and it also has a regularizing effect, since the mean and variance depend stochastically on the mini batch. So which other pictures or images are in the batch will influence what the mean and variance per channel is for that batch. So L2 regularization no longer has a significant regularizing effect on any layer that's followed by batch norm, because if you decay your weights and then simply rescale everything, you're undoing the regularization, although that affects the learning rate. But batch norm itself gives you regularization, so it's okay. You don't need the L2 normalization when using batch norm. So in summary, batch norm improves gradient flow, allows higher learning rates, reduces strong dependence on initialization, and acts as a form of regularization. So if you go back and look at the ResNet architecture that we covered a couple of weeks ago, you'll see that it applies batch norm after each convolutional layer, which improves accuracy and speed. All right. So there's another method of regularization called dropout, where at each training stage, each node is randomly kept with probability p, and you do this by generating a binary mask, and you multiply the activations by the mask. And so this is also a form of regularization. It forces the network to be not too reliant on any given neuron or feature, and hence it's less likely to overfit idiosyncrasies of the training data. Dropout, you see used mostly on fully connected layers. It wouldn't really make sense, for example, to use it on convolutional layers where the spatial relationships encoded in the features map make activations correlated by construction. So, for example, we see in VGG where they had those fully connected layers with over 100 million parameters that they use dropout. Whereas subsequently, when they got rid of the fully connected layers, you see ResNet using batch norm. All right. So if you want to test and do model inference using the full network and you've trained using batch norm, you'll need to either scale down at test time or scale up during training. Okay. A final thing to mention in terms of normalization is data augmentation, which is, when we say data augmentation, we mean you transform your data such that the labels are preserved. And so examples include random crops, flips, randomly varying contrast and brightness, rotate, stretching, lens distortion. We see data augmentation used, I think, a lot more in vision examples than in NLP, where there's these kind of very nice distortions that you can apply to images. Okay, and well, why is data augmentation a form of regularization? Well, you're forcing your model to learn that this image contains a dog, even when you do these distortions to the image, like cropping it, flipping it, stretching it, etc. So again, it's forcing the model to become more robust to essentially to noise in your underlying data. And data augmentation gets used in a lot of contexts, and so we'll see this more as we move into talking about applications. Okay, setting hyperparameters. And so if you're training a model, you'll need to have 3 partitions of your data: train, validation, and test. The validation set is used to evaluate hyperparameter estimation, whereas you only use your test data for reporting results. And if you're using an existing benchmark, it will pre-specify each of these sets. And so you'll need to cross-validate across hyperparameters. And generally the most important hyperparameter is the learning rate along with the architecture itself. And so you see here this tweet, which is meant to be a joke because there is no best learning rate. It's going to really depend on your application. You might think, well, okay, I need to choose my learning rate. I'll do a grid search. That's generally a bad idea. And you see that shown here, which compares doing a grid search to doing a random search. And so it's typically going to be the case that one hyperparameter may be really important and other hyperparameters will be less important. And if you do a grid search, then you have fewer values of the important hyperparameter to look for variation in, right? And so you'll tend to do worse than if you did just a random search. So you can potentially begin with a coarse search for the learning rate, and then can do a finer search. You'll need to sample in log space because the learning rate is multiplicative. Once you have a good sense of the general learning rate, you can worry about things like adding a learning rate schedule. So what do I mean by that? Ideally, you'd like to combine different learning rates, slowing down as you approach the minimum. And that's what a learning rate schedule does. And so this is an example of a learning rate step decay, where in steps, as you go through training the model, you're decaying the learning rate as training advances. So an alternative approach, which has really taken off recently, is using Bayesian optimization to choose your hyperparameters, which can be combined with early stopping. So it's straightforward to implement in weights and biases. And you can essentially use a bandit style approach to choose your learning rate. So this is what grid search would be, and you can see that it is not getting us close at all to the local minimum here. We do a bit better with random search, but then when we do Bayesian search, we stop early in hyperparameters that it's clear are not optimal, and we do more searches in areas of the space where it gets better results. All right, so the learning rate is an important hyperparameter. Bayesian optimization can potentially be used, and it's very straightforward to do that in weights and biases. And I'd really recommend in general using weights and biases. In practice, models are often not that sensitive to reasonably chosen hyperparameters, fortunately. So as long as you have something that's reasonable, oftentimes it doesn't make that much of a difference. Okay. Finally, monitoring the learning process. You'll want to plot your loss and plot your accuracy. A big gap between train and validation accuracy suggests overfitting, which means you might want to increase regularization. All right. And the one other thing that I would recommend with regards to monitoring the learning process is, again, that weights and biases have tools that make it much easier to monitor your training runs and keep track of everything that's going on. All right, you can find a lot more suggested tips and tricks online and in the literature. So for example, there's a paper Bag of Tricks for image classification with convolutional neural networks that has some helpful rules of thumb. These rules of thumb may be directed at ImageNet. Your mileage may vary on something else, but they can still be kind of helpful to keep in mind. So for example, when we get to object detection, we'll talk about some of the rules of thumb for choosing hyperparameters there. Regardless, if you look, at this paper, if you go to use a model, in Hugging Face, it might have a discussion of it, and there could be some useful information there. It might give you a sense of things that are helpful to have in mind as you choose your hyperparameters and try to optimize the model more generally. Okay, so just to sum up, data preprocessing, that's straightforward. Weight initialization, if you're probably initializing with something pre-trained. If you have some weights that need to be randomly initialized, you can use the He et al. Initialization. Optimization, you would use either stochastic gradient descent with momentum or ADAM, which combines stochastic gradient descent with momentum with RMS prop. Typically you would use batch normalization. That's already going to be built into the architecture that you're using. So it's not like you turn on and off the batch normalization in ResNet. It's just a part of ResNet. But it's good to know that that's there. Other regularization methods could be used as well. Regularization methods will interact with each other in the optimizer, which is important to keep in mind. And follow best practices when optimizing hyperparameters. Consider using the hyperband capabilities that are available in weights and biases. All right, thanks. I'm really looking forward to talking more about all of this in class on Tuesday.